In this video, I'm going to go over the invertible matrix theorem, which is a fun theorem because there are so many conditions that are equivalent to a matrix being invertible that just the statement is huge. This is the statement. Let A be an n by n matrix. Then the following are equivalent. The very first condition of this theorem is A, that the matrix A is an invertible matrix. That is, of course, equivalent to the definition of invertibility, which means that there is an n by n matrix B such that B times A is equal to the identity and A times B is equal to the identity. Now, because of how transposes work, then that is equivalent to the transpose of A being invertible. And moreover, by the way we compute the inverse of a matrix, we know that being invertible is equivalent to A being row equivalent to the identity. Meaning that if I do row operations, elementary row operations to A, and I'm able to get to the identity in its row reduced echelon form, then A is invertible. And in that case, that being row equivalent to the identity is equivalent to the echelon form for A, any echelon form or the row reduced echelon form having n pivots. Now, since the matrix is n by n, having n pivots is equivalent to having a pivot in every column, which is equivalent to the system, the equation, the matrix equation A times x is equal to 0, having only one solution, the trivial solution, because there will be no free variables, and that is because there is a pivot in every column when we row reduce the matrix A. Now, that is equivalent to the columns of A being linearly independent, which is also a condition that we check by making sure that there is a pivot in every column in an echelon form for A. And the columns being independent, linearly independent, means that the transformation, the linear transformation given by the matrix A, T of x is equal to A times x, is 1-to-1, injective. Now, if an echelon form of A has n pivots, it also means that there is a pivot in every row because A is n by n. And when that happens, that is equivalent to the matrix equation Ax equals B to have a solution for any fixed B in Rn. And therefore, what that means is that the columns of A span every single element of Rn, which can be expressed if and only if the matrix map, the matrix transformation Tx is equal to Ax is onto all of Rn. And so you can see that there are so many conditions that are equivalent to a matrix being invertible that this theorem becomes really useful when working with matrices because we can use many different conditions in many different ways to deduce properties of matrices that are invertible or to prove that a matrix is not invertible because one of these fails.